on. So our last speaker for the afternoon before the discussion is Raleigh Hood. You're going to talk to us about boundary currents.
Okay. First, I'd like to thank the OCB Steering Committee for making this session, this Indian Ocean session, possible. Excuse me, and giving us a chance to talk about some of these really crazy and interesting dynamics in the Indian Ocean. What I'm going to do today is talk about some of the biogeochemical and ecological impacts of boundary currents specifically in the Indian Ocean. And this talk is based on a review paper that hopefully will be coming out in Progress in Oceanography this fall. And I have to acknowledge my co-authors, Lyneth Beckley and Jerry Wiggert, who have made huge contributions to this paper and to this presentation. And so this is my outline. And what I was going to talk about, a lot of what I was going to talk about has been talked about. This is a review paper. But I will repeat some introduction to boundary currents in the Indian Ocean, focusing specifically on the boundary currents. I was going to talk about some of the biogeochemical and ecological impacts of the reversing boundary currents in the northern Indian Ocean, and I'll add a little bit to what's already been discussed, but I'll probably move through some of this fairly quickly because a lot of it's already been discussed. I was going to talk about the poleward flowing Lewin current and its anomalous biological signatures, but Anya just talked about that. So we'll kind of slide through that. But I've got the Agulhas current. Nobody's talking about the Agulhas current. So yeah, maybe we'll just focus on the Agulhas current. But I do have some nice animations to show you, which I think you'll find interesting, and will, I think, add to some of the things that have been talked about. So, as Waji and others have said, the Indian Ocean is really different, okay? It's bounded to the north by the Eurasian landmass. That landmass drives the intense monsoon winds. I think also importantly, the northern basin is divided in half by the Indian subcontinent, which gives, as has been discussed by Dennis, some very different properties between the Arabian Sea and the Bay of Bengal, and also mentioned by Waji. We have the porosity, the Indonesian through flow, as part of the global thermohaline circulation, the surface return circulation of the global haline circulation, okay? And these are the features, from my point of view, make the Indian Ocean unique. Now, what I'm going to show you now is an animation. And it's a little tricky to start and stop it where I want it. But this is a GFDL high-resolution coupled model 2.4 simulation. What you're seeing is temperatures. Of course, warm colors are warm temperatures. Cold colors are cold temperatures over the Indian Ocean. This is a time counter, so you can watch where we are in the seasonal cycle as we move forward. And where we're starting is in the winter between December and January. So we're smack dab in the middle of the northeast monsoon. So this is the time period where we have, as everybody's talked about, we have these cold, dry air coming down over the northern Indian Ocean. And I want to emphasize that it's not just the Arabian Sea, it's the Bay of Bengal as well. You can see the cooling. And I want to emphasize that in terms of the context of the boundary currents, these winds tend to drive, make sure I get this right, cyclonic circulations. They tend to drive downwelling circulations. The boundary currents tend to be downwelling during the northeast monsoon, okay? So let's run this forward and watch it. We'll run on into the spring intermonsoon, and you'll see the effect of the relaxation of the monsoon winds, the northeast monsoon, and you'll see that the northern Indian Ocean is going to start warming up as those winds relax, getting warmer and warmer and warmer. And this is the transition to the spring intermonsoon time period where we go from a productive situation to a stratified near-oligotrophic situation, okay? All across the northern Indian Ocean. Again, I emphasize this is happening not just in the Arabian Sea, but also in the Bay of Bengal. So let's run this forward. Let's run it into the southwest monsoon, and you'll see the southwest monsoon spinning up to repeat. There's the Tibetan Plateau. You get this intense heating off of the Tibetan Plateau, and that hot air rises, and the fin ladder jet goes woof across the western Arabian Seas. So here we go. If I can find my controls. So we start to see the spin up of the upwelling off of Somalia, off of Oman, getting really intense, and I want to stop this there. Okay? And so we've emphasized the upwelling in the Arabian Sea. Obviously, man, it's intense upwelling in the Arabian Sea. But I also want to emphasize, as Waji mentioned, there's also upwelling occurring. These are generally anticyclonic upwelling. The boundary currents all become generally anticyclonic upwelling favorable currents throughout the Arabian Sea and in much of the Bay of Bengal. And you can see that signature very strongly off the southern tip of India and off of Sri Lanka. So let's just let it run through a little bit. And you can watch this circulation and the upwelling. We're coming into the fall intermonsoon. Now we're heating again, back to oligotrophic conditions. Now coming back into the winter, the northeast monsoon. You see that cool, dry air cooling the entire northern Indian Ocean. And then the northeast monsoon relaxes, and we come back to this oligotrophic situation. So now I want to draw your attention to the Java current. I'm going to talk a little, I will be mentioning a little bit about the Java current. The Java current also reverses seasonally, and I think you'll see some upwelling signatures. The Java current flows to the west during the southwest monsoon, to the east during the rest of the year, basically. And when it's flowing to the west, it's the southern hemisphere. It's an upwelling favorable situation. We'll talk a little bit about that. And then also I want to draw your attention to the Lewin current, the ITF. We have this huge amount of warm water coming from the western Pacific, creating, as Anna mentioned, the high pressure of this area. It's driving the Lewin current south. Okay, so that's why the Lewin current goes south. We have this high pressure situation, and you can just see a really nice, see the Lewin? It's kind of small. It's a little guy, but you can see it going into the cool water to the south. We also have the south equatorial current bringing this water across the basin and then feeding into the Agulhas current through the Mozambique Channel and the East Madagascar current. And I'll show you another animation from this model simulation later that we'll take a look at the Agulhas current. Okay, so again, Jerry showed this, but maybe I'll give you just a little bit more detail. These are the basic current structures contrasting the southwest monsoon to the northeast monsoon. Okay, and as Jerry pointed out, and I'll start on the west side. During the southwest monsoon, we have the East African coastal current, which is upwelling favorable. That's northern hemisphere. In the winter, it reverses and becomes the Somalia current. In the southwest monsoon, we have strong, rather disorganized flows, but they're upwelling favorable. Okay? In the winter, they are also kind of disorganized, but generally more downwelling favorable. We have in the summer, the southwest monsoon, we have the West Indian coastal current, East Indian coastal current, both upwelling favorable. In the winter, they reverse and become downwelling favorable. Southwest monsoon, we have the southwest monsoon current coming across the southern tip of India and Sri Lanka, upwelling favorable in the southwest monsoon, downwelling favorable during the northeast monsoon. And then in the Java current, we have the Java current during the southwest monsoon. In this part of the world, it's called the southeast monsoon. Upwelling favorable, as I mentioned previously, flowing to the west, the southern hemisphere, upwelling favorable, and reversing only during sort of the late southwest monsoon and fall period. And then the rest of the time, it's flowing in the opposite direction, and it's a downwelling favorable current. Okay? So let's see. So all of the northern Indian Ocean currents reverse partially or fully in response to the monsoon winds, and they tend to be upwelling favorable in the southwest monsoon, and they tend to be downwelling favorable during the northeast monsoon. Most of these currents are relatively small. Many of them are on the order of about 10 spherodraps, and their transverse are different depending on which way they go. The biggest one is the Somali current, order 30 spare drops, but still, these aren't huge currents. But some of them, like the Somali current, are very fast. As we all know, as what we've seen, the local wind forcing is very important, especially associated with upwelling favorable winds during the southwest monsoon, but also remote forcing impacts by coastal Kelvin waves are very important in the northern Indian Ocean. And I believe Jerry mentioned this. And what we get these, Mike mentioned the Worky jets. We get the Worky jets generated in the spring and the fall. And when those Worky jets generate planetary waves that come across the equator, they hit Sumatra, they split. Some go north as coastal trap Kelvin waves, some go south. And the ones that go north make it all the way around the Bay of Bengal, come all the way around Sri Lanka, and get all the way into the Arabian Sea. And what those waves do is they can have very counterintuitive effects on the coastal flows. And they can cause flow reversals and switching from upwelling and downwelling in opposition to the wind. So you can get some really weird stuff happening in the coastal currents associated with the propagation of these Kelvin waves. So let's see. Okay, well, we've talked about this. Dennis did a really nice job of explaining the seasonal dynamics of productivity in the Arabian Sea, the upwelling, the intermonsoon relaxation, oligotrophy, and then this cooling and entrainment of nutrients in the northeast monsoon. And the point I want to add to that is that it also happens in the Bay of Bengal. This is happening in the Bay of Bengal too, but you can't see it very well. And the reason you can't, there's two reasons. You can see it, right? You see the upwelling. Look at the difference between this, and you can see there's upwelling response. You get coastal upwelling responses, but there's two reasons it's weaker. It's weaker because the winds are a bit weaker, and as Wadji pointed out, the salinity cap. There's all this fresh water on the surface in the Bay of Bengal, and there is upwelling, what you might refer to as cryptic upwelling, where that upwelling is happening, but it can't get through that boundary, that surface freshwater boundary. Okay? So I wanted to add that to that discussion. We can go forward. This is going to save some time. I was going to talk about the iron and silica limitation story, but I want to reiterate it because I can add one more thing to that story. So that it's this notion that the pioneering work by Jerry Wiggert, who predicted that the Western Arabian Sea transitions from N to FE limitation, turned out to be true. How many years later? 10 years later. And Wadji Naqvi has argued, as Jerry mentioned, that this turns into a high nutrient, low chlorophyll situation, which is really remarkable. And so the one thing I want to add to that story, which actually Mike Landry mentioned just a little earlier this afternoon, and it's Sharon Smith's grazing story, okay? And so in addition, we get higher trophic level responses. We get zooplankton responses to these changes in productivity. And we have this guy, Calanoides carinatus. Sharon is still studying this organism off some small island off of Oman. And what happens is these guys, somehow they know when the bloom's going to happen. They come up, they anticipate the bloom, and they graze. Okay, and so they're impacting, they're grazing, they're having a grazing impact in high nutrient, low chlorophyll, iron limited, silica limited water. And where have we heard that story before? Eastern equatorial tropical Pacific. Okay, so you have the emergence of this whoa, what's going on here? We've got iron and silica limitation, and maybe grazing going on, and maybe we don't understand that balance. And we had that discussion earlier in response to Mike Landry's question. So I wanted to add that little bit to that story, and I would say that story is pretty open-ended right now. And just another little anecdote that we also see behavioral responses in much bigger, higher trophic level organisms like the kingfish. It's an important historical fishery off of Oman where they come in at the beginning. They come in just before the southwest monsoon. And then they spawn once a year, right before the southwest monsoon, let those eggs go, and I don't know where they go, but for obvious reasons, they release their eggs just before the bloom, okay? So we get higher trophic level responses as well. And so in the paper, we talk about a whole bunch of other stuff. We talk about one of the Waji's story that he hit on earlier about the role of boundary currents and upwelling in augmenting this massive hypoxic zone off of the west coast of India. We talk about the upwelling induced during the southwest monsoon off of Sri Lanka, which gives rise to very high chlorophyll concentrations and also is manifest at higher trophic levels and catch per unit effort and things like that. We talk about the upwelling that occurs along the coast, this cryptic upwelling. It's damped, weaker winds, fresh water, and how there's not a lot of higher trophic level data in this area that I could find, but there is evidence of responses in the zooplankton community during the upwelling period, the southwest monsoon, more zooplankton changes in the community structure. And we also talk in the paper about the Java current. I just mentioned that the Java current during the later southwest monsoon and fall period is upwelling favorable. That upwelling produces a really strong productivity response. And we also see zooplankton behavioral responses, some evidence of zooplankton behavioral responses that look kind of like what Sharon Smith has been seeing in the Arabian Sea. These zooplanktons coming up and perhaps, it's not clear, anticipating the bloom, and also even higher trophic level responses like sardines and increases in sardine catch in the Bali Strait. So that's what I have for the northern Indian Ocean. So let's move on to the Lewin Current. I'll recap a few things that Anya said about the Lewin Current. It's the only poleward flowing eastern boundary current in the world, okay? Right? Eastern boundary currents everywhere else flow equatorward, all right? Okay? The Peru current, Canary current, California current. So, and as I mentioned, the Lewin Current flows south due to the pressure head created by the ITF. That's why it goes south. And Anya talked about the source regions coming from the ITF, the Eastern Gyral Current, the South Equatorial Current, and also there's sources coming from the tropical Indian Ocean. The Lewin Current is small. It's a little current. It's only about 300 meters deep, and it's less than 5 spare drifts. Okay, it has significant seasonal variability. It's stronger in the winter, but it doesn't reverse like the northern Indian Ocean currents do. It's always flowing south, and as Anya mentioned, it's a downwelling favorable current because, as the students will note, the Coriolis effect is to the left in the southern hemisphere. So that current is bumping up against the coast of Western Australia, driving downwelling. It's strongly remotely forced, as I've mentioned, by the high pressure associated with the ITF. But there is local wind forcing that can lead to little pockets of upwelling, mostly in the summer and some in specific headlands. But they're small, transient upwelling events. And the transport of Lewin is also influenced by remote forcing, by planetary Kelvin waves. I've mentioned that those Kelvin waves coming across the equator split. Some go south, and those can influence the transport of the Lewin Current. And also the ENSO can influence. ENSO it tends to be inversely related to ENSO. So the Lewin Current tends to be stronger during La Nina. Okay, and as Anya has already talked about, it has very high kinetic energy, generating a lot of eddies down here that creates what she's talked about, these productive warm core eddies and jets. Okay, but I'll kind of skim over that because she's really covered it. But I want to show you an animation, a little entertainment here, and so this is ocean. This is Australia. This is a eddy resolving model simulation from Australia's ocean forecasting model. And again, we're looking at temperature. Warm colors are warm water. Cold colors are cold. And we'll just zoom in here, and you can in toward the in the ITF region. This flow coming in from the Pacific, warm fresh water, as Anya mentioned. I'm going to stop it right there. We can revisit you can see that Java current upwelling. This is during the southeast monsoon, or the late southwest monsoon, going into fall. You get that strong upwelling signal off of Java. Java. And now let's go and follow some of this warm water coming down along the coast. You can see the eddies and feeding into this. The Lewin current is realized as this warm, small current going down the coast. And then it generates a whole bunch of eddies. It has really high kinetic energy. And these are some simulation warm core, high chlorophyll eddies like Anya just talked about. Okay? And I was going to talk about those eddies, but I don't really have anything more to add than what Anya's already said. There's one. This is from her 2007 paper. But only to add that they're really weird, right? Warm core, high chlorophyll eddies? What's with that, right? So that's kind of neat. So I will leave it at that. And I will just mention, Anya also talked about the rock lobster. But I don't think she mentioned that there's that historically there's a very strong tie. She talked about the settlement of these Parulus larvae, and historically there's been this really strong tie between the Lewin current transport and the settlement of these larvae. And this is indicated by sea level is a proxy for the strength of the current, right? Sea level's high means you have a steep slope, geostrophy, strong flow. And you can see there's a really strong link. So when you have these strong flows, for some reason, which is not understood, the strong flows are delivering these larvae more effectively to the southern coast of Australia. And so somehow, when these currents are strong, they're bringing these larvae down, maybe taking them offshore, and then bringing them back in, and they're getting back into the coast to settle. And you get strong recruitment years when the flows are large. But for some other species, like coastal anchovies, these eddies that we see propagating offshore, these coastal anchovies have been found in there. My colleague, Lyneth Beckley, has studied these, and they're being taken offshore, and they're gone. They're dead. They're food for some other organism, okay? So that's what I've got for the Lewin current. So let's now go way over to the southwestern side of the basin and talk about the big beast, the Agulhas current. A few properties of the Agulhas current. It's a warm, southward western boundary current in the southern hemisphere. It has source regions. Its source has 3 source regions. They're from the Mozambique Channel. They're from the East Madagascar current, and also from the subtropical gyre that's contributing to the Agulhas current. It's very deep. Its signature can be seen down to over 1,000 meters. It's very big, arguably the largest boundary current, eastern boundary current in the world, order 80 spheredreps, depending on where you slice it. It's upwelling favorable, and my physical oceanography friends don't like it when I say that, and that's why I put it in quotes. But the reason that I say it's upwelling favorable, because again, we're talking about the southern hemisphere, right? Southern hemisphere, Coriolis effect to the right, that current is getting pulled away from the coast, okay, and it's tipping the isotherms and the isopycnals and the nutricline up toward the surface. But surface manifestations are primarily realized through wind, upwelling favorable winds, which happen during the southern hemisphere summer, and also topographic interactions. When that big current interacts with the topography, sometimes it induces upwelling, okay? And let's see, what else? Another interesting property, so the Lewin current, we get all these seaward propagating eddies and filaments. The Agulhas doesn't really do that at all. It doesn't produce things that go east, okay? But it does produce alongshore propagating eddies, and we'll talk a little bit about that. Okay, they're called they're eddies that originate around Durban and the Natal Bight, so they're called Durban eddies and Natal pulses. And obviously the Agulhas current is strongly remotely forced because it is the surface, it's the western intensified boundary current of the southern subtropical gyre of the Indian Ocean. Okay, it's a huge part of the southern circulation, southern Indian Ocean circulation. Okay, and I'll just throw this up here to give you a little bit of a sense of what the chlorophyll looks like. This is just an average sea whisk chlorophyll for no particular year. And what you can see is that you can see this upwelling effect, and getting on the inshore side of the current comes right along here, and I'll show you an animation of it in a little bit. And you can see the upwelling effect and the increased chlorophyll. And this area here is called the Agulhas Bank. And you can see, and the current is starting to move off of the shore. And you can see the broadening of this area where you get the enhanced chlorophyll. But again, this is primarily associated with winds and topographic forcing. No seaward eddies. And as you'll see in I'll show you some animations of these cool eddies that roll down the coast of the south of South Africa. The story with fisheries, higher trophic levels in the Agulhas Current, is that if you're a coastal fish, like a sardine, an anchovy, a horse mackerel, and you do not want your progeny getting in the Agulhas Current. Because if your progeny get into the Agulhas Current, or if you get into the Agulhas Current, you're gone, okay? They'll end up in an Agulhas ring and end up in the South Atlantic and die there, or go into the retroflexion and end up in the Southern Ocean, and they'll certainly die there. So all of these coastal species have evolved similar types of strategies, where what they do is that they spawn on the inshore side, just inshore of the Agulhas, just kind of in the safety zone. And over the Agulhas Bank, you get these recirculation features that take those larvae and they move them up and up into these particularly productive upwelling zones further north and east on the Agulhas Bank. And remarkably, some of these species, like the South African pilchard, after it spawns, for reasons which I don't think anybody knows, it itself swims up and goes all the way up to up near Durban and the Natal Bight, and it does this upstream of the Agulhas Current, and which would seem, and this has been a question that scientists from South Africa have pondered for quite a while, and I think they think they know the answer, and you may have heard of it. It's called the Kwazulu-Natal Sardine Run. I'm almost done, too. It's called the KZN Sardine Run. It happens in the southern hemisphere fall and winter, okay? And you get billions of sardines after they spawn running up the coast of the Agulhas Bank in the face of the Agulhas Current. And this sardine run has a really remarkable higher trophic level impacts. You get dramatic responses. Everything feeds on them: sharks, birds, dolphins, whales, and even people. So the question is, how do they do this? And the short answer is that through a combination of, in the winter, you get some northward winds that facilitate northward flow very close to the coast, but you also get these eddies that propagate southwestward along the coast, but they create recirculations as they go. They're like wheels spinning down the coast, and they create reverse circulations, okay? And so they create, this is an example of one of these eddies. It's an elongated eddy. It's moving like this, okay? And it's causing enhanced northward circulation inshore. And then you can see the huge Agulhas Current offshore. This is the Agulhas. And then here's a section. You can see the Agulhas here flowing south, but this is a north. This is the recirculation going backwards. And that's the spin axis of that eddy. So it looks like they use the wind to help them go north, but then maybe they hang around and wait for one of these big eddies to come, and they dash up the coast. So that's the idea that's being put forward by one of my colleagues, Mike Roberts. Okay, so let's see. I can't go into everything we talk about in the paper, and I really am almost done, Mike. We talk about Mozambique eddies, their productivity effect, their effect on higher trophic levels like great frigate birds. We talk about the topographically forced upwelling off the southern tip of Madagascar, which leads to enhanced productivity, higher trophic level response. And we also talk about the effect of the Agulhas Current on biogeographical distributions of zooplankton, and where we find that the Agulhas Current is bringing tropical Indo-Pacific species all the way down onto the Agulhas Bank. So let's wrap it up with one more animation where I can show you some of the things that I've been talking about. This is the same GFDL model. And we'll start it up here. So we have the source regions Mozambique Channel, East Madagascar Current, and the subtropical gyre feeding into the Agulhas Current, which much of the time flows in a well-behaved, sort of straight manner, like that, okay? But not always. And then you can see this cold water coming up, the upwelling of the Agulhas Bank as the current is moving offshore. And then sometimes it generates these alongshore propagating eddies, these coming from the vicinity, it's coming from up in this area up here, okay? And if you watch it, you'll see these form. And let's see, that might be one. Yeah, that's one, it's a little one. I think this is a big one. Comes down, and this one actually changes the trajectory of the retroflexion. See that? So anyway, those are the kinds of things I've been talking about. I'll stop that. And I'm not going to read those. And so that's the end of my talk. And I don't know how Jerry and Mike want to handle this. I do have a couple of slides on the IIOE2, but I know I'm out of time.
Yeah, well, perhaps we can just go into a Q&A and if they come up.
We could do that. Okay.